Good morning. We're in this second unit about descriptive statistics, and this is another video where I will talk about box and whisker plots. This is a kind of plot which is very useful in statistics. So let's start with this set of example. So imagine that I have just 9 values. So here I'm indicating the average, median, and different parameters. Okay. So this is the shape of the box and whisker plot. Well, so important. Remember that I'm just building this plot with 9 values, which is a very small sample size. But the shape of this box and whisker plot is symmetric. So the main advantage of this plot is that it provides information about the type of distribution when the sample size is small. For example, here the shape is more or less symmetric, so I can say that the type of distribution is symmetric. So how is this box and whisker plot? Okay, if the shape is symmetric, I can say that the distribution is symmetric, and quite likely it could be normal distribution. Okay, so useful when the sample size is small. So how is it obtained? Well, this is called the box. Okay, the line inside the box corresponds to the median, 191. So the left end of the box is the first quartile here, 175. The right end of the box is the third quartile. Okay, and then these are called whiskers. It is called the left whisker, and then it is called the right whisker. Okay, so the end of this left whisker is the minimum, the end of the right whisker is the maximum. Okay, so based on this shape, as it is symmetric, we can think that the data can be assumed as a sample from a normal distribution. And interestingly, if we check the values from the standardized skewness and kurtosis coefficients, both of them are comprised between -2 and 2. And so in the previous video, I was explaining that this was a rule to conclude that the sample can be considered as obtained from a normal distribution. Okay, this is a different example. In this case, I have just 10 values, which again is a small sample size, but the shape of the box and whisker is very different. Okay, well, so the box is the same, so it is obtained using the same criteria. So the line inside the box corresponds to the median. Here, the median is 4. At the right end of the box is the third quartile. The left end of the box corresponds to the first quartile. This is the minimum value, and this is the maximum value. Okay, so this is the typical shape of a box and whisker for a positively skewed distribution. But also this shape, okay, this kind of plot provides information to say if the skewness, if the degree of skewness is slight, moderate, or strong. Okay, in this case, it is not slight. We can say that it is like moderate or strong. Okay, but in this case, not slight. Well, so also the box and whisker plot has a rule which is implemented to visualize the extreme values. This rule will be explained in the next slides, but in this case, so the maximum is not the end of the right whisker, because there is a rule to visualize that this value is much separated from the next value, which is positioned here. Okay, so what are the rules to conclude that the skew is positive? So there are 3 rules. The first one is the right whisker is longer than the left whisker. In this case, the right whisker is longer than the left whisker. The second rule is that the median is not centered in the middle of the box. No, it moves to the left. We can see here, the median is not here in the center, it moves to the left. Okay, and the third rule is that we can see a few isolated points, but on the right side. Here we can find an isolated point, but only here on the right side. Okay, So here we can conclude that there is a positive skew, and interestingly, if we take a look at the standardized value of the skewness coefficient, it is 2.5, which is bigger than 2. I explained in the previous video that this is a very common rule to conclude that the skewness is positive. And then this would be a typical type of box and whisker for a negatively skewed distribution. It's the same, but inverting the plot. Okay, so let's talk about this rule to visualize extreme values. Okay, I call them as isolated points. So first, I put the position of the first quartile, of the median, and the third quartile, and then it gives me the box. Okay, this is the box. Then the difference between the third quartile and the first quartile is the interquartile range. Okay, then I go to the third quartile, which is the one. Okay, and I add 1.5 times the interquartile range, and here it gives me like an imaginary limit. I don't draw this limit, but I have to remember that this limit exists and it is there. Okay, so if the maximum value is on the left of this imaginary limit, this value will be the end of the right whisker. Good, and then I do the same on the left. So I take the first quartile minus 1.5 times the interquartile range. And again here, I will have like an imaginary limit that I don't draw, but it is there. So if the minimum value is outside this limit, it is represented as an isolated point. Then I go to the second minimum value. In this example, as this value is on the right side of this imaginary limit, this value will be the end of the left whisker. Okay, so this is the rule. And the median sometimes is represented as a point or a small cross inside the box. Okay, so generally speaking, the box comprises 50% of the values from the first to the third quartile. Okay, the central line corresponds to the median, as I have explained. So the whiskers extend from the lowest to the highest observed value, except if their distance is bigger. If their distance to the nearest quartile is bigger than 1.5 times the interquartile range, as I have just explained. Okay, so this rule is to visualize extreme values, and then we have to decide or to determine if those values are outliers to be removed, or if we should keep these values because they are not erroneous values to be removed. So those extreme values that differ from the nearest quartile more than 1.5 times the interquartile range are plotted as isolated points, but not indicating that they should be removed. No, it is just to highlight that they might be outliers, but we need to apply other criteria to think if they are outliers to be removed or not. Okay, so if we can have extreme, so erroneous data, abnormal, atypical, outlier, extreme. So in statistics, we use different names, and everybody can apply a slightly different concepts. But the key issue is that should we remove that value, yes or no? And this is the key issue, because if a value is clearly erroneous and that does not correspond to the population, we should remove it, because otherwise it will affect too much to the average, to the variance, and many other parameters of position and dispersion. Okay, so we should remove the value if it does not belong to this distribution. Okay, so if the distribution, if the probability to belong to this distribution is very low. Okay, and then I'm going to discuss it with an example. This example is the same that the one that I used in a previous video. Okay, imagine that I have the salary of the employees of 10 people working in a small company. So this value is not erroneous. It corresponds to the salary of the boss. Okay, so I should not remove it. It corresponds to a positively skewed distribution. And actually, if I have the data of salary in a big company we can see more clearly that this is a typical example of positively skewed distributions. Okay, so once again, we will define in this unit as an outlier as an abnormal value that does not belong to the population, that lies out of the rest. So if I'm sure that a value is a clear outlier, there has to be eliminated. If the value is just a slight or moderate outlier, then we can decide to maintain it. Okay. So, but I will define as extreme value those values that appear with low frequency on the extremes of the distributions. For example, in the case of a positive skewed distributions, those isolated points on the box and whisker will be called extreme values. Okay, so not all isolated points appearing in the box whisker plots are outliers to be removed. Okay, then another rule is that in a normal distribution, all isolated points in the box whisker appearing quite close to the end of the whiskers may not be outliers. Okay, actually, we can compute mathematically the probability of a value to be higher than the end of the right whisker. That probability is 0.003. It is small, but not too small. So if I have a lot of values, we may find a few values. Okay. So then, what is the best method to identify outliers to be removed in the case of a positively skewed distributions? Well, so my advice is to represent the data on a normal probability plot using different kind of transformations. First the square root, then the fourth root, and then the logarithmic. So the normal probability plot will be explained in detail in another video, but as it is useful here, I will talk about it somewhat. For example, imagine that this is a box whisker with the values of time to arrive at university. I have the values of 131 students. And then I have a value of 90. So one student answered that he took 90 minutes to come to the university and 90 minutes to go home. So is it an outlier? Should we remove this value or not? Okay, well, so now I'm going to make a normal probability plot, and although I will explain this in a further video, it works as following. So if the data fit to a straight line, we can say that data come from a normal distribution. But if the data follow a curve like this, like in this example, it is a clear curve, so it corresponds to a positive skew. Okay, well, so in this case, this is time with any transformation. This is the square root of time, and I can find that still there is like a slight curve. But if I apply the fourth root of time, we can see how the values fit very clearly to this straight line. So if the fourth root of time fit to the line, then we can say that they come from a normal distribution, and the maximum value fits also to the line. So the maximum value is not an outlier, is not a value. So we can say that this maximum value belongs to the same distribution. So we should not remove that value. Okay? So as all transform values fit to a normal distribution, we don't have outliers to be removed. Okay. Then I'm going to explain this exercise. So how can we make a box and whisker plot with these values? The first step is to sort them from the lowest to the highest. Then we identify the value which is in the center, which is the median. Then the first quartile is the value in the third position. The third quartile is the value here. Then based on this information, I already have the information to build the box. Okay, so upper limit, upper imaginary limit. We take the third quartile plus 1.5 times the interquartile range. So this imaginary limit is in the position 63, okay? So you can see how this would be the imaginary limit. Okay, then I take the highest value, 90. As this 90 is higher than the imaginary limit, it is plotted as an isolated point. Now I go to the second highest. the second highest is 50. 50 is here, as it is on the left of the imaginary limit. It is the end of the right whisker. So the minimum is 2, and 8, 16, and 30 are used to build the box. So this is the box whisker. So about the distribution, the shape clearly corresponds to a positively skewed distributions. The 3 rules are accomplished. Remember, right whisker is longer than the left whisker. The median is not centered, it moves to the left, and we find 1 isolated point. Is this skewness slight, moderate, or strong? I will say slight or moderate, not too strong. Is there any outlier to be discarded? Probably not. We should make this procedure, but probably the maximum value is not an outlier. Okay, now I'm going to talk what is called multiple box and whisker plots. Okay, for example, imagine that here I have the height of a set of students. Some of them are men, some of them are women, so the code 1 corresponds to men, the code 2 corresponds to women, and then here we can see clearly the differences. Okay, the median of women is very different to the median of men, and also the interquartile range. Okay, so the range of most frequent values is totally different. This multiple box and whisker was obtained with real data. Okay, so this is very useful comparison, and this kind of comparison is not possible with histograms. Okay, so sometimes in the exams we put some kind of box like this, and we can ask different questions. For example, calculate the interquartile range, calculate the range of women's, describe the distribution. Okay, for example, in the case of men, this is quite symmetric. Okay, but in the case of women, look that this is longer than the left. The median moves slightly to the left, and there are a few isolated points. So we have the 3 rules to conclude that there is a slight positively skewness. But in the case of men, it is not. And what about the presence of outlier? Okay, so these values are not outliers to be removed because the distribution is slightly positively skewed. But in this case, as the distribution is more or less symmetric, it can be assumed as normal. So in a normal distribution, those values that deviate very much to the end of the whiskers are outliers to be removed. So these values are a clear outlier, but these 2 values not so clear because they are close to the end. Okay, this is another example of a multiple box and whisker. In this case, we had a continuous variable, which was the height. So the values of height were divided into intervals, and then we build a multiple box and whisker plot. Okay, here we can see that there is an increasing trend, so that when the height increases, the weight also tends to increase. Okay, this will be used in another unit, in another video, to explain the concept of conditional distributions. Okay, so here we finish this video about box and whisker plots. Thank you for your attention.